right? So what this means is that in order to use this notion of pi, we need to think of things a little differently, okay? We need to think of, we can think of a function, we can start out by thinking of a function, and indeed we do need to think of a function because a function is involved in here, right? We do have u, which is drawn from a certain function space, right? So if this is x, right, and our domain is 0 to L, right? This is our domain omega, right? This is our domain omega. On this domain, we do indeed have a displacement field, right? It's a function, right? And recognizing the sort of boundary condition we have at x equals 0, let us set u equal to 0 there, and then we may have something like that, right? Okay, so that could be our displacement field, right, in one dimension. Now, when we have a displacement field of this type, okay, we get a particular value for pi, okay? So from here, you may think of now constructing this mapping to pi of u, right? Note, however, that in order to calculate pi of u with this value, with this particular displacement field, you need to know the displacement field over the entire domain because we need to integrate, right? Now, if instead of this displacement field, we were to have a different field, which I will use green for, right? So you may have some other field, right, also satisfying the same boundary condition, but perhaps our field is this one, right? And from here, we would get a different pi of u. Maybe I should call this u2 and the original field u1. Okay, that is u2 maybe, and this original field is perhaps u1. Okay, so it's critical to understand that in order to calculate each value of pi, right, a single scalar value of pi, you need the entire field. All right, so in this sense, this is fundamentally different from a function which you can evaluate with just a point value of the argument. Okay, all right. So what we see is that pi is, in this way, it's fundamentally different from a function. It is what gets called a functional. Okay, in this, because anything that takes as its argument an entire field is a functional, and clearly an integral is a functional, right? There is another object, a very familiar object, that is also properly defined a functional. Can you think of what that might be? It's closely related to an integral, actually. A derivative, right? Strictly speaking, a derivative is also functional because you cannot evaluate a derivative with just a point value, right? Properly defined, a derivative needs a field description, right? You may have a formula for a derivative, right? But in order to obtain that formula, right, in order to even define a derivative, you actually need a field. Okay, so pi. So all right, so pi is a functional, all right, and this is the functional we're going to work with. Okay, so this is the setting, and let's proceed from here. So pi is functional. In particular, it is it can be called, and this is the term I will use for it. It is in fact our free energy functional. Right, okay, the Gibbs free energy functional. Okay, all right, okay, so what can we do with a free energy, right, or an energy, an energy in general, but particularly a free energy? There is a certain commonly used technique or principle, if you want to call it that, that is often invoked when we have a free energy. Can you think of what that is? Yes, it's the idea of minimizing or extremizing free energies, right? So, extrema of free energies characterize, and why do we bother with extremizing free energies? It's because extrema of free energies characterize states of equilibrium of systems. Okay, and therefore there is this interest in calculating extrema of free energies. Okay, and I'm going to draw the very common picture, which I'm sure you've all seen in either in high school or early on in your college careers. It's the idea that, well, if you have a free energy, right, with respect to some variable, and just not to confuse things with anything else, I'm going to denote the variable as y. Let's suppose our free energy here is F, right, or our energy is F. We know these kinds of notions, right, that at extrema, right, there are our system is at equilibrium, right. So we may have that, we may have a different extremum there, and then we may have that type of an extremum as well. Okay. So at each of them, we know that f prime is equal to 0, right, as well as here, right? And we know that when f prime is equal to 0, we're at an extremum, right? So each of these are extrema. They're also understood as points of equilibrium, right? So these are, so f prime equals 0 are okay. And then, of course, we can go on to the notion of second order extremum conditions and make statements about which of these extrema are which of these extrema have equilibria that are stable or unstable or metastable or neutrally stable and so on, right? We can go on and have that discussion, right? So let me just put that down, right? So typically f double prime, let me see. So if f double prime is greater than 0, we have a stable equilibrium. Right? If f double prime is less than 0, we have an unstable equilibrium. And if it's equal to 0, we have a metastable, or probably more widely called a neutrally stable equilibrium. Right, and they are characterized by these three these 3 points in the curve. Right, this is all standard, fairly straightforward stuff. So, well, this is all standard and straightforward stuff, but the question obviously arises, can we do the same thing for our free energy functional pi, right? So, can we find extrema of, I'm sorry, I have a slightly recalcitrant pen today. Can we find extrema of pi? Right, and clearly, once if we can find extrema of pi, we can make all these statements about the system being at equilibrium, stable, unstable, and so on. Right, and so our main task is, can we find extrema of pi? The answer is yes, yeah, we can, of course. But is it straightforward? Do you know directly how to do it? Well, sort of, yes, if you think about it. We know if a function is sufficiently smooth, we can define its derivative, and its derivative is what gives us notions of extrema, right? Where the derivative vanishes is what gives us an extremum. And that's what we saw on the previous slide. The same sort of thing would apply to pi as well. If pi can be sufficiently smooth as a functional of u, we can indeed find extrema, right? Assume that it is smooth, right? The question then remains, what do we mean by a derivative, right? And the challenge here is the following. What is an appropriate notion of, I'm going to write it out in words, right, of a derivative of pi with respect to WRT for with respect to u. Okay? Question mark. What is an appropriate notion for this? Why is this not obvious? Why is this not something that we can directly inherit from our conventional notion of derivatives of functions? Well, because we really need to say what it means to differentiate a functional, which is a set of real numbers, right? It maps into the space of real numbers. We need to talk of what it means to differentiate it with respect to an entire field. Okay? And this is not that straightforward if you think about it. Right? In fact, unless you already know how to do it, it should not be obvious to you how to do it. Okay, so so we are really talking here of differentiation with respect to a field. Right, the field being u in this case. Right, we need to appropriately define this notion. Okay, if we can define this notion, we can actually make progress towards talking about extrema and states of equilibria and so on. Okay, we are going to do that, but this is a good place to end this segment. We'll come back and define this notion of a functional derivative.